Imagine a star so distant its light has crossed the universe for 13 billion years, captured by James Webb sensors as a faint, eerie red glow. Scientists call it the Little Red Dot, a mystery that's puzzled astronomers since 2022. Now, a newly discovered object, a black hole star lurking in the cosmic dark, may hold the key. This stellar remnant, forged in the first generations of stars, is so far away its existence defies current models of galaxy formation. How could such a distant, ancient star emit the same reddish light Webb saw? Could it be a hidden signal from the universe's infancy, a beacon from the era when galaxies first ignited? The answer might lie in this bizarre celestial ghost, a black hole star so far, so old, so strange, it could rewrite our understanding of how the cosmos lit up. In the vast expanse of the universe, where light has traveled billions of years to reach us, scientists have made a discovery that could rewrite our understanding of the cosmos. For the first time, astronomers have identified the farthest black hole star ever observed, a celestial object so distant that its light has taken over 13 billion years to reach Earth. This finding, announced recently, is not just a record-breaking achievement, it holds the potential to unravel one of the most intriguing mysteries from the James Webb Space Telescope's first images, the so-called Little Red Dot. But what exactly is this object, and why does its discovery matter? Let's dive into the story of how this distant light might help us understand the early universe and the enigmatic glow that first captured our attention. To grasp the significance of this discovery, we need to start with the basics. A black hole star isn't a literal star, but rather a term used to describe a supermassive black hole surrounded by a glowing disk of gas and dust. These objects, known as quasars, are among the most luminous entities in the universe. They form when a supermassive black hole at the center of a galaxy pulls in surrounding material, heating it to extreme temperatures and emitting vast amounts of energy across the electromagnetic spectrum. Quasars are so bright that they can outshine entire galaxies, making them visible even from the edges of the observable universe. The little red dot that stunned astronomers when the James Webb Space Telescope first captured its image was one such quasar. Located about 13.1 billion light-years away, it appeared as a faint, reddish speck in the telescope's early data. At first, scientists were puzzled by its appearance. Why did it look so red? Why was it so far away yet still visible? The answer lies in the nature of light and the universe's expansion. Light from distant objects is stretched over time due to the universe's expansion, a phenomenon called redshift. The more distant an object, the more its light is shifted toward the red end of the spectrum. This redshift is a key tool for measuring cosmic distances, but the little red dot posed a unique challenge. Its extreme redshift suggested it was among the earliest objects ever formed, yet its brightness hinted at a massive energy output. How could such a distant object be so luminous? This was the mystery that the new discovery might help solve. The newly identified black hole star, a quasar named GNZ11, pushes the boundaries of what we thought possible. Located approximately 13.4 billion light-years away, it is the farthest quasar ever observed. Its light, emitted when the universe was less than 500 million years old, has traveled through the cosmos for over 13 billion years to reach us. What makes this discovery remarkable is not just its distance, but its brightness. GNZ11 is so luminous that it outshines the entire Milky Way galaxy. This extreme brightness suggests that the supermassive black hole at its center is actively accreting material at an unprecedented rate, releasing energy that rivals the output of thousands of stars. Such a quasar would have played a crucial role in the early universe, influencing the formation of galaxies and the distribution of matter. But how does this discovery connect to the little red dot mystery? The answer lies in the study of quasars and their evolution. The little red dot quasar, which scientists initially struggled to interpret, was thought to be a young, massive quasar. However, its extreme redshift suggested it was even older than GNZ11. By comparing the properties of these two distant quasars, astronomers can begin to piece together the timeline of supermassive black hole formation. The existence of GNZ11 implies that such massive black holes could have formed much earlier than previously believed, challenging existing models of how these objects grow. If supermassive black holes can form in the first few 100 million years of the universe, it suggests that the processes driving their growth, such as mergers of smaller black holes or the accretion of gas in extreme conditions, were more efficient than previously thought. The implications of this discovery extend beyond the study of quasars. The little red dot and GNZ11 are part of a broader puzzle, the role of quasars in the early universe. These objects are thought to have played a critical role in shaping the cosmos. Their intense radiation may have ionized the intergalactic medium, a process known as the cosmic reionization. This period, which occurred around 500 million to 1 billion years after the Big Bang, marked the transition from a dark, neutral universe to one filled with ionized gas and star-forming regions. Quasars like GNZ11 and the little red dot could have been key contributors to this transformation, providing the energy needed to ionize hydrogen atoms and pave the way for the formation of the first galaxies. However, the discovery of GNZ11 also raises new questions. How did such a massive black hole form so quickly? Current theories suggest that supermassive black holes grow over billions of years through mergers and accretion, but the existence of GNZ11 implies that this process may have started much earlier. Some researchers propose that these black holes could have formed from the direct collapse of massive gas clouds, bypassing the slower growth through stellar remnants. Others suggest that the early universe's unique conditions, such as higher density fluctuations or the presence of dark matter halos, may have facilitated the rapid formation of these objects. The study of GNZ11 and similar quasars is helping scientists refine these theories and test the limits of our understanding of black hole formation. The connection between GNZ11 and the little red dot also highlights the importance of the James Webb Space Telescope in uncovering these distant objects. Unlike previous telescopes, JWST's advanced instruments allow astronomers to peer further into the universe and study the properties of these ancient quasars in greater detail. The little red dot was one of the first images JWST returned, and its mysterious appearance sparked a wave of curiosity and debate. Now, with GNZ11's discovery, scientists have a new benchmark to compare against. By analyzing the light from these quasars, researchers can determine their mass, luminosity, and the composition of their surrounding environments. These data provide critical insights into the early universe's structure and evolution, helping to bridge the gap between theoretical models and observational evidence. As we piece together the story of these distant quasars, it becomes clear that they are more than just luminous beacons in the cosmos. They are windows into the universe's infancy, offering glimpses of a time when the first stars and galaxies were forming. The little red dot and GNZ11 are part of a growing catalog of ancient quasars, each contributing to our understanding of how the universe evolved from its chaotic beginnings to the structured cosmos we observe today. By studying these objects, scientists can trace the history of supermassive black holes, the role of quasars in cosmic reionization, and the processes that shaped the first galaxies. The discovery of GNZ11 is a testament to the power of modern astronomy and the James Webb Space Telescope's ability to peer into the universe's distant past. It reminds us that the cosmos is still full of surprises, and that each new observation brings us closer to answering the fundamental questions about our origins. As researchers continue to analyze the data from these ancient quasars, they may uncover even more mysteries, perhaps even ones that challenge our current understanding of physics. For now, the little red dot and its distant counterpart GNZ11 stand as reminders of how far we've come in exploring the universe and how much further we have to go. The James Webb Space Telescope has been hailed as a revolutionary tool for peering into the cosmos, but even it has its limits. For years, scientists have struggled to observe the earliest galaxies in the universe, those that formed just a few 100 million years after the Big Bang. These ancient structures, often referred to as the little red dot mystery, are faint, distant, and shrouded in the cosmic fog of the early universe. Now, a groundbreaking discovery may be providing the key to unlocking this enigma. Scientists have identified the farthest black hole star ever observed, a quasar powered by a supermassive black hole, located over 13 billion light-years away. This object, detected using the James Webb Space Telescope and other advanced instruments, could offer critical insights into how the first galaxies formed and how black holes grew in the early universe. But how exactly did researchers find this distant beacon, and what methods allowed them to confirm its existence? Let's walk through the process that led to this discovery. The journey began with a combination of cutting-edge technology and decades of accumulated knowledge about the universe. The James Webb Space Telescope, launched in 2021, is designed to observe the cosmos in the infrared spectrum, a wavelength that allows it to peer through the cosmic dust and gas that obscure the earliest galaxies. However, even with its advanced capabilities, detecting objects at such extreme distances requires a unique approach. Scientists had to rely on a technique known as redshift, which is a fundamental concept in astronomy. As the universe expands, light from distant objects is stretched into longer wavelengths, a phenomenon known as the Doppler effect. By measuring this redshift, astronomers can determine how far away an object is. The more distant the object, the greater the redshift. For the black hole star in question, the redshift was so extreme that it suggested the object was among the earliest galaxies ever observed. But identifying such an object isn't as simple as pointing a telescope at a distant point in the sky. The challenge lies in distinguishing between genuine cosmic signals and background noise. The James Webb Space Telescope's instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, are designed to capture faint light, but even these tools can struggle with the sheer distance and brightness of the earliest galaxies. To overcome this, scientists employed a method known as multi-wavelength astronomy, which involves combining data from different telescopes and instruments that operate at various wavelengths. This approach allows researchers to cross-check observations and filter out false positives. For example, the Hubble Space Telescope, which has been in operation since 1990, has already provided valuable data on distant galaxies, while the Spitzer Space Telescope, which operated until 2020, offered infrared observations that complemented Hubble's data. By integrating these observations, scientists could build a more complete picture of the distant universe. The discovery of the black hole star was made possible by a combination of advanced imaging techniques and sophisticated data analysis. One of the key tools used was the James Webb Space Telescope's ability to capture high-resolution images of distant objects. The telescope's large mirror, which is nearly 3 times the diameter of Hubble's, allows it to collect more light from faint sources. This is crucial for observing objects that are billions of light-years away. However, even with this advantage, the process of identifying a potential candidate for the black hole star required careful analysis. Scientists had to sift through vast amounts of data, searching for objects that exhibited the characteristics of a quasar. Quasars are among the most luminous objects in the universe, powered by supermassive black holes that accrete matter and emit intense radiation. These objects are often surrounded by a torus of gas and dust, which can make them appear as bright, point-like sources in the sky. However, their extreme distance means that even the most luminous quasars appear as faint specks of light, making them difficult to distinguish from other celestial objects. To confirm the presence of a quasar at such a great distance, scientists had to use a combination of observational techniques. One of the most critical methods involved measuring the object's redshift. By analyzing the spectrum of light emitted by the quasar, researchers could determine how much the light had been stretched due to the expansion of the universe. This process requires highly sensitive instruments capable of resolving the fine details of the light spectrum. The James Webb Space Telescope's NIR-SPEC instrument, which is designed to capture spectra of distant objects, played a key role in this analysis. By breaking down the light into its component wavelengths, scientists could identify specific spectral lines that indicate the presence of elements like hydrogen and oxygen. These spectral signatures are crucial for confirming that the object is indeed a quasar and not some other type of celestial body. Another important step in the confirmation process was cross-referencing the data with existing astronomical databases. Scientists used catalogs of known galaxies and quasars to compare the new observations with previously recorded data. This helped rule out the possibility that the object was a previously identified galaxy or a foreground star. Additionally, the team used machine learning algorithms to analyze the data, allowing them to identify patterns that might indicate the presence of a quasar. These algorithms were trained on vast datasets of known astronomical objects, enabling them to recognize the unique characteristics of quasars even in the most challenging conditions. The timeline of the discovery also highlights the collaborative nature of modern astronomy. The James Webb Space Telescope's mission is part of a broader effort to study the early universe, and its findings are often combined with data from other observatories. For example, the European Southern Observatory's Very Large Telescope, VLT, in Chile and the Atacama Large Millimeter/Sub-Millimeter Array, ALMA, have contributed to the study of distant galaxies by providing complementary data. These ground-based telescopes operate at different wavelengths and can observe objects that are not visible to space-based instruments. By combining data from JWST with observations from these ground-based telescopes, scientists can create a more comprehensive understanding of the early universe. The confirmation of the black hole star also required careful consideration of potential observational biases. One of the challenges in studying distant galaxies is the possibility of contamination from other light sources. For example, the light from a nearby galaxy could be mistaken for the light from a distant quasar. To mitigate this, scientists used a technique called photometric redshift, which involves measuring the brightness of an object at different wavelengths to estimate its distance. This method, while less precise than spectroscopic redshift, provides a valuable initial estimate that can guide further observations. By combining photometric redshift data with spectroscopic analysis, researchers could more confidently determine the object's distance in nature. In addition to these observational techniques, the discovery also relied on the development of new data analysis tools. The sheer volume of data collected by the James Webb Space Telescope requires advanced computational methods to process and interpret. Scientists have developed specialized software to handle the massive datasets, allowing them to identify and analyze potential candidates for distant quasars. These tools are essential for navigating the vast expanse of the cosmos and uncovering hidden structures that may have been overlooked by earlier telescopes. The significance of this discovery extends beyond just identifying a distant quasar. By studying the properties of this black hole star, scientists can gain insights into the formation and evolution of the earliest galaxies. Quasars are thought to have played a crucial role in shaping the early universe, as their intense radiation may have influenced the formation of stars and the distribution of dark matter. Understanding how these objects formed and evolved could provide answers to some of the most fundamental questions in astrophysics, such as how the first galaxies formed and how supermassive black holes grew so quickly in the early universe. The process of discovering and confirming this distant quasar is a testament to the power of modern astronomy and the collaborative efforts of scientists around the world. It highlights the importance of advanced technology, innovative data analysis techniques, and the integration of data from multiple observatories. As the James Webb Space Telescope continues its mission, it is likely to uncover more such distant objects, further expanding our understanding of the universe's origins and evolution. This discovery not only brings us closer to solving the Little Red Dot mystery but also underscores the incredible capabilities of the James Webb Space Telescope in unraveling the cosmos' deepest secrets. Farthest black hole star ever found could help solve the James Webb Space Telescope's Little Red Dot mystery. This part of our deep dive into farthest black hole star ever found could help solve the James Webb Space Telescope's Little Red Dot mystery focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For centuries, humanity has gazed at the night sky, wondering about the nature of the cosmos. From the earliest stargazers to modern astronomers, our understanding of the universe has evolved dramatically. But until the 20th century, the idea of black holes, regions of space where gravity is so intense that not even light can escape, was purely theoretical. It wasn't until Einstein's theory of general relativity in 1915 that scientists began to seriously consider the possibility of such objects. Einstein's equations suggested that if a massive star collapsed under its own gravity, it could form a singularity, a point of infinite density, surrounded by an event horizon. This concept was initially met with skepticism, but as the 1930s progressed, physicists like Subrahmanyan Chandrasekhar and John Wheeler began to explore its implications. By the 1960s, the discovery of quasars, intensely luminous objects powered by supermassive black holes, began to shift the paradigm. These quasars, observed at vast distances, hinted that black holes might be more than just theoretical curiosities. They were real, and they were at the centers of galaxies, their immense gravitational pull shaping the evolution of entire star systems. Yet, even with these breakthroughs, the universe remained a mystery. The tools to study it were limited, and the faintest signals from the farthest reaches of space were often lost in the noise of cosmic background radiation. Enter the Hubble Space Telescope, launched in 1990. For the first time, astronomers could peer into the early universe with unprecedented clarity. Hubble's images revealed distant galaxies, some of which were forming just a few 100 million years after the Big Bang. But there was a problem: the light from these galaxies was so faint, and the data so sparse, that many questions remained unanswered. How did galaxies form? What role did black holes play in their development? And what about those mysterious red dots observed by the James Webb Space Telescope? These dots, which seemed to glow with an eerie red hue, defied easy explanation. Were they stars, planets, or something entirely new? The answers, it turned out, might lie in the study of black holes, specifically, a newly discovered object that could be the farthest black hole star ever observed. To understand this, we need to look back at the history of how we've come to see the universe. The 1970s and 1980s saw the rise of radio astronomy, which allowed scientists to detect the faint radio emissions from distant objects. These observations led to the discovery of active galactic nuclei, the bright cores of galaxies powered by supermassive black holes. But even with these advances, the universe remained a vast, uncharted territory. The 1990s brought the Hubble Space Telescope, which revolutionized our ability to study distant galaxies. Hubble's images revealed that the universe was not as uniform as previously thought. Instead, it was a patchwork of structures, with galaxies forming in clusters and superclusters. However, Hubble's resolution was limited, and it could not detect the faintest objects, especially those at the edge of the observable universe. This is where the James Webb Space Telescope, JWST, came into play. Launched in 2021, JWST was designed to observe the universe in the infrared spectrum, allowing it to peer through the dust that obscures visible light. Its primary mirror, 6.5 meters in diameter, is the largest ever deployed in space, enabling it to capture light from the earliest galaxies. But even with JWST's capabilities, some mysteries remained. One of the most intriguing was the so-called little red dot phenomenon. These dots, observed in the early data from JWST, appeared as faint, red-hued objects in distant galaxies. Their exact nature was unclear. Were they young stars, dying stars, or something entirely different? The red color suggested they were emitting light at longer wavelengths, possibly due to the expansion of the universe stretching their light into the infrared. But the faintness of these objects made it difficult to determine their true nature. Enter the latest discovery, a black hole star found at an unprecedented distance. This object, which appears to be a black hole surrounded by a luminous accretion disk, could be the key to solving the mystery of the little red dots. But how did we get to this point? The journey to understanding black holes and their role in the universe has been long and winding. In the 1960s, the first black hole candidates were identified through X-ray emissions from binary star systems. These systems, known as X-ray binaries, consist of a normal star and a compact object, often a neutron star or a black hole. The X-rays are produced as material from the normal star is pulled into the compact object, forming an accretion disk that emits intense radiation. These observations provided the first evidence that black holes exist in our galaxy. However, the true scale of black holes became apparent in the 1980s and 1990s, when astronomers began to study the centers of galaxies. The discovery of quasars, which are powered by supermassive black holes, showed that these objects could be millions or even billions of times more massive than the Sun. But how did these black holes form? Theories suggested that they might have formed in the early universe, when gas clouds collapsed under their own gravity, or that they grew over time by merging with other black holes and accreting matter. These theories were supported by observations of galaxy mergers and the detection of gravitational waves from black hole collisions. Yet, even with these insights, the role of black holes in the formation of galaxies remained a topic of debate. The 2000s brought a new wave of discoveries, including the detection of gravitational waves by LIGO and Virgo in 2015. These ripples in spacetime, predicted by Einstein's theory, confirmed the existence of black holes and provided a new way to study them. The detection of black hole mergers allowed scientists to measure their masses and spins, offering insights into their formation and evolution. But while these discoveries were groundbreaking, they still didn't answer the question of how black holes influenced the formation of galaxies. This is where the latest findings come into play. The discovery of a black hole star at such a great distance could provide crucial clues. If this object is indeed a black hole surrounded by an accretion disk, its luminosity could be similar to the little red dots observed by JWST. The red color might be due to the intense gravitational redshift caused by the black hole's immense gravity, stretching the light into the infrared spectrum. Moreover, the distance of this object suggests that it formed in the early universe, when the cosmos was still young. Studying such an object could help scientists understand how supermassive black holes formed and how they influenced the growth of galaxies. But to fully appreciate this discovery, we need to consider the broader context of how our understanding of the universe has evolved. The 20th century was a golden age for astronomy, with the development of radio telescopes, space-based observatories, and advanced computational models. These tools allowed scientists to map the universe in ways previously unimaginable. Yet, even with these advancements, the universe remained a vast, mysterious expanse. The 21st century brought new challenges and opportunities. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, has opened a new window into the early universe. Its ability to detect faint, distant objects has allowed astronomers to study the first galaxies, stars, and black holes. But the data from JWST is still being analyzed, and many questions remain. The little red dots, for example, could be the result of a variety of phenomena, from young stars to exotic objects like primordial black holes. The discovery of a black hole star at such a great distance adds another piece to the puzzle. It suggests that black holes may have played a more significant role in the early universe than previously thought. However, this is just the beginning. As scientists continue to analyze JWST's data, they may uncover even more surprises. The universe is vast, and our understanding of it is still in its infancy. But with each new discovery, we come closer to unraveling its mysteries. The journey to understanding black holes and their role in the cosmos is far from over. It is a journey that has spanned centuries, driven by curiosity, innovation, and the relentless pursuit of knowledge. And as we look to the future, the possibilities are as endless as the stars themselves. The James Webb Space Telescope has captured one of the most perplexing images in cosmic history, a faint, red glow from the early universe, so bright it defies current models of galaxy formation. This little red dot, a term coined by scientists to describe the unexpectedly luminous light from the first galaxies, has sparked a firestorm of debate. How could such ancient galaxies emit so much energy? What processes powered them? And why does their light appear so intense, even from such a distant time? These questions have haunted astronomers since JWST's first images, but a recent discovery may offer a tantalizing clue: the farthest black hole star ever found. This object, a supermassive black hole nestled within a young galaxy, could be the key to unlocking the mystery. Yet, even as this discovery shines a light on the past, it raises new questions about the very nature of cosmic evolution. Let's explore what this means and what it still leaves unanswered. The little red dot mystery centers on the early universe, a time when galaxies were just beginning to form. According to standard models, these nascent galaxies should have been dim and diffuse, their light struggling to pierce the cosmic dark ages. But JWST's observations reveal a different story. The light from these ancient galaxies is not only present but overwhelmingly bright, suggesting they were producing energy at rates far beyond expectations. This brightness is puzzling because it implies the galaxies were either incredibly massive, unusually efficient at converting matter into light, or harboring some exotic energy source. The little red dot is not a single object but a collective glow from countless distant galaxies, each contributing to a luminous tapestry that challenges our understanding of how the universe evolved. Enter the farthest black hole star ever discovered. This object, identified through JWST's advanced infrared capabilities, is a supermassive black hole residing in a galaxy that formed just a few 100 million years after the Big Bang. Its existence is significant because such massive black holes typically form in environments where galaxies have had ample time to grow and accumulate gas. Yet, this particular black hole appears to have formed in a galaxy that was still in its infancy, raising questions about the conditions that allowed it to grow so quickly. If this black hole is indeed the source of the little red dot light, it would mean that these early galaxies were not just forming stars but also harboring supermassive black holes capable of emitting vast amounts of energy. However, the connection between this black hole and the observed glow remains speculative. Scientists are still debating whether the black hole itself is the source of the light or if it is merely a companion to a more luminous galaxy. One of the most pressing questions is how such a massive black hole could form so early in the universe's history. Supermassive black holes are typically thought to grow over billions of years, gradually accreting gas and merging with other black holes. But the black hole discovered by JWST appears to have reached a size that should take hundreds of millions of years to develop. This discrepancy has led to a flurry of hypotheses. Some researchers suggest that these black holes may have formed from the direct collapse of massive gas clouds, bypassing the usual stellar evolution processes. Others propose that they grew rapidly through intense accretion events, fueled by the dense gas surrounding them. However, these theories are still in their infancy, and the mechanisms behind such rapid growth remain poorly understood. The discovery of this black hole adds a new layer of complexity, suggesting that the early universe may have harbored conditions that allowed for the formation of these massive objects in ways we have yet to comprehend. Another layer of uncertainty lies in the relationship between the black hole and the galaxy it inhabits. While the black hole's presence is significant, its role in the galaxy's luminosity is still unclear. Some scientists argue that the black hole itself is the source of the intense light, emitting radiation as it accretes gas. This process, known as active galactic nucleus (AGN) activity, can produce enormous amounts of energy, outshining the stars in the host galaxy. However, the observed brightness of the little red dot suggests that the light is coming from the galaxy itself, not just the black hole. This has led to the hypothesis that the galaxy may have been unusually rich in gas and stars, allowing it to produce light at an unprecedented rate. Yet, the exact mechanisms behind this extreme luminosity remain a mystery. Could the galaxy have been a prodigious star-forming region? Or was it the result of some other phenomenon, such as a collision between galaxies or the presence of dark matter? The debate over the little red dot also extends to alternative explanations for its brightness. Some researchers propose that the light we observe is not from the galaxies themselves but from the intergalactic medium, the vast, diffuse gas that fills the space between galaxies. This gas, if heated by the intense radiation from early galaxies, could emit light that appears as a diffuse glow. However, this theory faces challenges. The intergalactic medium is expected to be extremely diffuse, making it difficult to account for the observed brightness. Moreover, the light from the intergalactic medium would have a different spectral signature than the light from galaxies, which could be detected through detailed analysis of JWST's data. While this remains a possibility, it has not yet gained widespread acceptance, and the search for definitive evidence continues. The discovery of the farthest black hole star also raises questions about the broader implications for our understanding of cosmic evolution. If these massive black holes formed so quickly, it could mean that the processes governing galaxy and black hole formation are more complex than previously thought. It might suggest that the early universe was a more dynamic and chaotic place, with conditions that allowed for rapid growth of these objects. However, this also challenges existing theories about the role of dark matter in galaxy formation, which is still a topic of intense research. Some scientists argue that dark matter could have provided the gravitational scaffolding needed for these early galaxies to form, while others suggest that the observed phenomena could be explained without dark matter altogether. These debates highlight the many unresolved questions about the universe's early history and the need for further observations. Despite these uncertainties, the discovery of the farthest black hole star represents a significant step forward in our quest to understand the early universe. It offers a potential explanation for the little red dot mystery, but it also underscores the complexity of the issues at hand. The interplay between black holes, galaxies, and the intergalactic medium is a tangled web of interactions that scientists are only beginning to unravel. As new data from JWST and other observatories continues to flow in, these questions will likely evolve. What is clear is that the universe is far more mysterious than we once believed, and the answers we seek may lie in places we have yet to explore. For now, the little red dot remains a beacon of curiosity, a reminder that even in the vastness of space, there are still secrets waiting to be uncovered. As we look ahead, the quest to unravel the mysteries of the farthest black hole star and its connection to the James Webb Space Telescope's little red dot will rely on a suite of upcoming missions and instruments designed to push the boundaries of our observational capabilities. These projects, ranging from space-based observatories to ground-based telescopes and gravitational wave detectors, will not only help confirm the significance of this distant object but also challenge or refine our understanding of the early universe. The journey begins with the James Webb Space Telescope itself, which, despite its incredible achievements, has already hinted at the need for deeper exploration. While its ability to peer into the cosmos has already transformed our view of the universe, its observations of the so-called little red dot, a faint, redshifted light from the early universe, have raised more questions than answers. This enigma, which suggests an unexpected abundance of light from distant galaxies, may be linked to the newly discovered black hole star. But to fully grasp its implications, scientists will need to gather more data, and that requires looking beyond the capabilities of JWST alone. Enter the Nancy Grace Roman Space Telescope, a successor to Hubble, set to launch in the mid-2020s. This telescope will carry a powerful wide-field camera capable of capturing vast swaths of the sky with unprecedented precision. Its primary mission is to map dark matter and study the evolution of galaxies, but its ability to detect faint, distant objects could provide critical insights into the black hole star's role in the early universe. By analyzing the distribution of light across millions of galaxies, the Roman telescope might reveal how these ancient structures interacted with the first black holes, potentially linking them to the mysterious red dot. Meanwhile, the Euclid mission, led by the European Space Agency, is set to launch around the same time. Euclid will focus on studying dark energy, the mysterious force driving the universe's accelerated expansion. However, its instruments are also designed to probe the distribution of matter in the cosmos, including the influence of massive objects like black holes. If the farthest black hole star is indeed a key player in the early universe's light production, Euclid's data could help determine how its gravitational effects shape the surrounding environment. These space-based observatories will work in tandem with ground-based telescopes, which are rapidly advancing in their ability to observe the faintest and most distant objects. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the largest optical telescope ever built, with a mirror over 39 meters in diameter. Its adaptive optics system will allow it to peer through Earth's atmosphere with near-infrared precision, potentially capturing detailed spectra of the black hole star and its host galaxy. Such data could reveal the star's composition, age, and interactions with surrounding matter, offering clues about how it formed and evolved. Similarly, the Giant Magellan Telescope, GMT, also in development, will complement these efforts by providing high-resolution imaging of distant celestial objects. Together, these ground-based giants will act as a second line of defense, cross-checking findings from space telescopes and filling in gaps where their observations are limited by atmospheric distortion. But the story doesn't end there. The field of gravitational wave astronomy is also poised to play a transformative role. Instruments like LIGO and Virgo, which detect ripples in spacetime caused by cosmic collisions, have already revolutionized our understanding of black holes and neutron stars. However, their sensitivity to low-frequency gravitational waves, generated by the mergers of massive black holes, could provide a new perspective on the farthest black hole star. If this object is part of a population of massive black holes in the early universe, its mergers might have produced detectable gravitational waves. By analyzing these signals, scientists could determine the star's mass, spin, and orbital characteristics, offering a unique window into its properties. Moreover, future space-based gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, are set to launch in the 2030s. LISA will be capable of detecting gravitational waves from supermassive black hole mergers, which could help trace the evolutionary history of these cosmic giants. If the farthest black hole star is part of such a system, its gravitational wave signature might provide independent confirmation of its existence and role in the early universe. These efforts will not only deepen our understanding of the black hole star but also challenge existing models of galaxy formation and cosmic evolution. For instance, if the object's light output is indeed linked to the so-called little red, it could imply that early galaxies were more luminous or that black holes played a more active role in shaping their surroundings than previously thought. This would require re-evaluating theories about how galaxies formed and how their central black holes grew. Conversely, if the data fails to confirm the connection, it might suggest that the little red dot is the result of entirely different processes, such as the collective activity of many smaller black holes or the presence of unknown astrophysical phenomena. The potential for such revelations underscores the importance of these upcoming missions. They represent a collaborative effort across disciplines, combining the strengths of space and ground-based observatories, gravitational wave detectors, and theoretical models. Each instrument brings a unique perspective, allowing scientists to piece together a more complete picture of the universe's past. However, the path forward is not without challenges. The vast distances involved mean that even the most advanced telescopes will struggle to capture detailed images of the farthest black hole star. Atmospheric interference, instrumental limitations, and the inherent faintness of these objects will require innovative techniques and persistent observation. Moreover, the data collected will need to be meticulously analyzed, with researchers working to distinguish between genuine signals and cosmic noise. This process will involve not only technical expertise but also a willingness to question existing assumptions. The scientific community will need to remain open to the possibility that the little red dot mystery may not have a single answer but instead reveal a complex web of interactions involving black holes, galaxies, and the fundamental forces of the universe. As these missions progress, they will also inspire new questions. For example, if the farthest black hole star is confirmed as a significant contributor to the early universe's light output, what does that mean for the timeline of cosmic history? Could it imply that the first galaxies formed earlier than previously thought, or that black holes played a more central role in their development? These questions will drive further research, ensuring that the quest to understand the universe is an ongoing journey rather than a destination. In the end, the discovery of the farthest black hole star is not just about solving a single mystery. It is about expanding the boundaries of what we know, challenging our assumptions, and uncovering the intricate dance of forces that shape the cosmos. The upcoming missions and instruments will be the tools that guide this exploration, each contributing a piece to the puzzle. As we await their results, we are reminded that the universe is vast, complex, and full of surprises. And in the quiet hum of distant stars, there may yet be more to discover. So there it is, the farthest black hole star ever found, a cosmic beacon from the early universe, could finally shed light on the James Webb Space Telescope's mysterious little red dot. Let me break this down. First, this object, likely a supermassive black hole powering a quasar, is so distant that its light has been traveling for over 13 billion years to reach us. That places it in the universe's infancy, a time when galaxies were just beginning to form and the cosmos was still a faint, glowing haze. The little red dot JWST spotted a faint, diffuse glow in the early universe has puzzled scientists because it doesn't match the expected brightness of young galaxies. But now, this newly discovered quasar might be the key. Its intense light, emitted when the universe was less than a billion years old, could explain the red dot as a relic of that era, a flash from a supermassive black hole's hunger. This discovery bridges a gap between theory and observation, offering a concrete example of how such objects might have contributed to the universe's early glow. Second, this finding challenges our understanding of black hole growth. Supermassive black holes are thought to have formed quickly in the universe's youth, but how? This quasar suggests that massive black holes could have emerged in the first billion years, influencing galaxy formation and starbirth in ways we're only beginning to grasp. Third, it highlights the power of JWST to peer into the cosmos' infancy. By detecting such distant objects, the telescope is rewriting our timeline of cosmic evolution, showing that the universe was already teeming with activity far earlier than we imagined. But here's the catch: this quasar's existence raises more questions. How did such a massive black hole form so quickly? What role did it play in shaping its host galaxy? And if this one is possible, how many more like it exist, hidden in the cosmic dark? These answers could reshape our models of galaxy formation and the universe's early history. So what does this mean for us? It means the universe is more dynamic and complex than we thought. The little red dot isn't just a puzzle, it's a clue pointing to a cosmos where supermassive black holes were active powerhouses, lighting up the dark and shaping the galaxies we see today. But the story doesn't end here. This discovery is just the beginning. As we refine our telescopes and models, we'll uncover more pieces of this cosmic puzzle. And that's why I'm here, to keep exploring, questioning, and sharing the wonder of the universe. If you've enjoyed this deep dive, hit that subscribe button for daily space revelations. And if you've got theories or questions about this discovery, drop them in the comments. The universe is full of mysteries, and every question brings us closer to the truth. Until next time, stay curious.